move through it. All right. Alrighty then. So this is the final exam review. So we'll be going over the fall 21 exam and maybe the spring one, maybe specific questions on the spring one. Since this was an online format, it's not really something that we'd see the formatting at least. So we'd see different types of questions and such. So we'll focus on the same modality of question that we'll be doing. So first things first, we have a test one topic, which is CRC generation and code word stuff. So if anyone forgot, I need my annotations. So for this one, we have a couple things. So he gave us our message to be transmitted right here and our generator polynomial here. So he can give you this in two ways, but the generator polynomial is normally given as a polynomial. Now you have to turn this into the actual like generator in polynomial in bits. So basically to transmit this, you look and you treat this as the least significant bit and move up from there. So if the least significant bit is a 1, then you start as a 1. If it's not there, then it's a 0. So we go up a power to x. So that means the next bit up is a 1. We go up a power to x squared. X squared is not present. Therefore, our next bit is a 0. And then we go up to x cubed, which is our highest power. And we see that it is a 1 because it is present. Another thing to note, the length of our transmitted code word will be equal in bit length to the highest polynomial order that you see. So in this case, since we have an x cubed, we should expect our message, our transmitted code word for our message to be 3 bits long. I feel like that 3 is
4 bits.
3 bits.
All right.
Because the highest order polynomial is 3. We have x cubed.
I thought it was that plus 1.
It should be 3. I'm pretty sure it's just the number. In the solution, it ends up being 3.
All right.
So it should be just that without any modifications to it.
Okay.
So now for actually computing this, it's really just modified exclusive OR operations. So it's really polynomial division, but it can be treated as exclusive OR. So we do this, which is our generator polynomial, and then we do our message, which is 1 0 1 0 1 1 0. Now, a lot of people like put stuff up here as they do it. I don't. It's pointless. It means nothing. So it's useless. I don't waste my time putting stuff on the top. I only care about what I drag down. So as you start with any division, 0 1 0 0 to begin, we draw our line and we perform it. Everybody knows what exclusive OR is. If it's the same, it's a 0. And if it's different, it's a 1. So all of this has just been wiped out. You don't actually drag zeros down. You only drag 1. Like once you find your first 1, you'll drag zeros down past that. But any leading zeros in a number are deleted from existence. You don't even need to put them there. So that's that. So now what we do is we drag down enough bits to do a full 4 divisions again, which means 1 1 0. Draw the new bar, 1 0 1 1. That is not where that bar is meant to go. It's meant to go here. Now we do the math, same as 0. First thing is a 1, that's a 0, that's a 1. Now, you have to then tag on extra stuff to finish it up. So in this case, you can just add on trailing zeros. I forget the rules for adding on like trailing numbers, but I'm pretty sure it doesn't matter if you add trailing 1s or trailing zeros, you should get the same answer. But just for simplicity's sake, it's better to just do the zeros. I remember one of the homeworks he had us like brute force check that you can add 1s or zeros and it's the same thing. But in this case, just add zeros, it's easier. So we have 3 down here, 3 bits that are accessible to us. We put on a 0, drag it down. Now we have a 0, do 1 0 1 1, draw the line, 0 0 0 1 here, and then we drag down 2 more zeros, and we're finished with a solution of 100, or 100 is our transmitted code word. How do you know when you're done? If you can drag things down forever, you're done when you have your last bit from your message has been dragged down, and then you drag down enough to do to bring it to the length that you should expect, which is 3 from the beginning, because the highest order polynomial is 3 bits or cubed, so it's 3 bits. So once you've dragged down the last bit, or once you, not really that. So the last bit was actually this, because we added this 0. So you drag down the last bit, it comes all the way down here. This is where the last bit from the actual message was, but it wasn't long enough to do another 4-digit division. So we add one more bit to do one more 4-digit division and yields us one last bit on our last 4-digit division, and then we attack on the zeros. So basically you have to perform one last 4-digit division and then add on the zeros to basically pad it to the length expected by the generator polynomial.
I think
That's
you're
how you
supposed
get
to
that.
pad it with the zeros first. Like when you write the number on your bracket, you're supposed to add the 3 zeros before you do any of the exclusive OR.
Yeah, you can.
That's the way I've always done it.
I just realized something. Did I do it faster than this guy? I might have been able to skip steps here. I don't know. Let's see. In the solution, he padded it with 3 zeros immediately, like you said. Oh, no, it is. I didn't draw these. Yeah. So Seth's right. The speedrun trick is to instantly pad it with the length of zeros you should expect from the generator polynomial. That should give you the guaranteed right answer. And then that's how you know to stop, basically. So we'll clear that doodle and move down to the next question. Assume node B receives the following code word. By using the CRC, does node B detect any bit errors? All right. So basically we should expect a remainder of 0. So we take the transmitted code word and our generator polynomial, and then we do 1 1 1 0 0 0 1 0 1. And then we do 1 0 1 1. Draw your line. 0 1 0 1. Drag a 0 down. We have 0 here. 1 0 1 1 0 0 0 0 0 1. Drag down 3 digits. 0 1 0 1 0 1 1 line. 0 0 0 1. Drag down another digit. 1. Well, we have a problem. There's already a remainder. That's as far as you go. For checking, if there's errors, you don't tag on numbers. You shouldn't need to. There should be a remainder of 0 if there's no errors. If you have to tag anything on, you're done. It's already a problem. So no tagging on for checking for remainders. There's a remainder of 1 1. Therefore, there was in fact a bit error. So you would write this and you could basically just say, remainder, therefore error. All right. That's all you got to do for that kind of question. Easy peasy. Scroll on down to this next stuff. TCP. No, not TCP, just some random non-existent protocol. All right. You're designing a reliable byte stream transport layer protocol, not TCP, to operate over a 1 × 10⁷ power bits per second network. So that's bits per second, keep your unit straight. And it is using a sliding window for flow control. So it's flow control. So keep that in mind too. Remember that operational principle. The time for keeping the transmission pipe full is taken to be the RTT of the network, which is 100 milliseconds. There's another quantity for us. Each number is the advertised window or sequence number. Each number in the advertised window or sequence number represents 4 bytes of data. So we can already see that he's trying to trick us up with confusing data units that are different from one another. So at some point, we'll have to convert one of these to the other. What is the minimum number of bits necessary for the advertised window field of your protocol header? Advertised window field. Provide this minimum number as a whole number so you can calculate blah, blah, blah. All right. So basically, the formula for advertised window is supposedly 2 advertised windows. So the advertised window is whatever power 2 is supposed to be raised to times this. So we need 4 bytes of data because each number in the advertised window represents 4 bytes. So we just add a scalar. So you can do this one of 2 ways. You can convert everything to bytes, or you can convert everything to bits. In his example, he converts it to bits, so I'll stick with that. So in converting 4 bytes to bits, it's just 4 × 8. And that's the scalar there. And he says that this must be greater than the delay, which we know is 100 milliseconds, -3, times the bandwidth, which we know is bits per second. And it's 1 × 10⁷. Now, the way you can know to keep this stuff straight is on this side, you should be getting bits as your unit. And on this side, you should be getting bits. So let's think about that. This is in seconds, and this is in bits per second. So when you multiply these, seconds cancel, you're left with bits, and you're looking peachy. So basically, you do this math, right? So you do this, which let's think about this. So if this is 100, just move this 1, 2. So you have 100 times 10 to the negative 3 is just, pretty sure it's just, is it 0.1 or 1? It's 0.1. So it's 0.1 times 1 times 10 to the 7th. So in reality, this is just 1 times 10 to the negative 1st, which means this is going to be 1 times 10 to the 6th then, I believe. So you take that, divide it by, what is this? That's going to be 32. So that's going to make a number. And then you take the, you have to do the power stuff. So what is it to bring the power down? It's ln, it's log base, whatever. So in this case, it should be log base 2 of the other side. Will give you AW, I believe. Let me confirm that with a calculator to make sure I'm not pulling shit out of my butt. Let's see. Where's my calculator? There it is. Just gotta do some quick maths here. So if we do 100 times 10 to the negative 3rd times 1 times 10 to the 7th power, that yields that. Divide it by 32, that yields that. And then we should be able to do log, not that, I want the funny log, where I can change the numbers. Math. Make sure you know where to find your log function, gamers. Log base 2 of this number. Yes. Okay. That's how you do it. So you do this equation, this setup, right? You bring it all down such that this is what it looks like. I mean, you could do this, but really you could say this is equal to or whatever. Just make sure that this is greater than at the end of the day. So we have, we'll call this quantity X, and we'll call this quantity Y, X over Y. So therefore you do. So you'll have a W is equal to log 2 of X over Y. Is how you solve for AW. The solution here is AW must be greater than 14.93. Therefore, just stick with 15 bits. That's why he says round up, because rounding up will always satisfy the greater than scenario here. So you're clean, basically. But let's say you got a solid number and it says AW must be greater than, and your solution when you solve this thing was 20 on the dot. Then you would have to say 21 because it has to be greater than it and it has to be a whole bit. So in case that happens, which is unlikely, but if it does, remember that you'd have to increase it 1. Otherwise, you're wrong. You'd be a bit off because it has to be greater than. So you'd be missing that last straggling number. You'd have a little bit of overflow. So you can't have that. So we'll clear that. So we actually had a question like this, I think on exam 2, if I'm not mistaken. Yeah, we did. We did have a question like this on exam 2. I think it was like question like 2 or 3. Oh, well, moving on. How would you, excuse me. How would you choose the sequence number size in accordance with the advertised window size determined in A? Well, as we said, AW is equal to 15 bits. If that's the case, then the sequence number must be greater than 2 AW. So basically, this isn't 2 times the amount of bits. This is 2 times the advertised window number. And the reasoning we do it this way, let's see. Each to RT2 the network, each number in the advertised window or sequence number represents 4 bytes of data. So the sequence number just has to be double the advertised window. I don't exactly remember why, but that's how he's running it. So in that case, that means we do the digit value of AW and then multiply it by 2. So basically what that means is you've raised it another power. So it's almost like increasing it a bit, but not quite. You can be just barely greater than 15 bits if you just bring it up to 16 bits, because that brings it right past that little overflow. So the sequence number must be 16 bits long in order to satisfy this. Bonk, bonk. All right. A network has end-to-end length of 1,800 meters with a propagation speed of the speed of light. The bandwidth of the link is 100 times 10 to the 6 bits per second, or 100 megabits. The maximum frame size being transmitted on this network is 1,000 bits, or 1 kilobit, or kilobyte. No, kilobit, not kilobyte. Even so. What is the one-way propagation delay for this network? One way is simple. You take the length in meters, and you divide it by the propagation speed, which we will say is c here. That's understood to be the speed of light. And this is in meters per second. How do you know you're right here? Well, meters divided by meters per second cancels the meters, leaves us seconds. So you know propagation delay time should be a unit of seconds. So this is how you can check yourself for any gaffes if you pick the wrong number for some reason. But even so, if you do 1,800 divided by the speed of light, you get 6 microseconds. That looks like a milli, but that's meant to be the mu. Something like that. Oh, well, 6 microseconds, said it out loud. So that's a simple one. These like network parameter questions are really gimmies in my opinion. Like this is what you should want to see on the exam. What is the transmission time for a maximum size frame on the network? So a maximum size frame was described to be 1,000 bits. And then we have the bandwidth to be 100 or really 100 megabits. What does that mean? Well, we take 1,000 bits, unit of bits, keep your units straight. That looks like a bits, something like that, divided by the bandwidth, which is megabits or megabits per second. So that is going to be 100 times 10 to the 6th power MBS, megabits per second. How do you know that you're right? Transmission time should have a unit of time, cancels bits here, leaves us with seconds again. So we're looking good. 1,000 bits divided by 100 megabits is approximately 10 microseconds for the transmission of the full frame, full max size single frame. That's good, no problems there, nothing tricky. Down here. Assume the CSMA/CD is used on this network and that the link, so this is collision detection and Ethernet system. If this were CA at the end, then that would be collision avoidance. You'd be expecting this to be an 802.11 or a Wi-Fi network. So it's used on this network, and that the link, in addition to the propagation delay, has a queuing delay of 20 microseconds. What is the smallest size frame in bits? Bits, he asked it for bits, so keep in bits, that can be used such that a transmitting node is guaranteed of detecting a collision. So this is a tricky one. You'd have to go back and look at some stuff in your slides to remember it, but we're going to get that down here. So basically your smallest size for collision detection is going to be this value X divided by your bandwidth, 100 megabits. And this is a greater than again. And then we have 2 times some parameters we've already calculated. 6, which was calculated to be the one-way propagation delay. Because for collision detection, you're detecting a one-way propagation of a signal sent out by one of the members of the network. That's how that propagation detection or collision detection works. Once a collision occurs, whoever the recipient of that collision is sends out a silencing message to the entire network telling everyone to shut up and wait for transmissions to clear up functionally. So that's where we get. So the first thing is we do 2 times 6, and then it should be plus 20. This 20 comes from the queuing delay. So that means this is going to be equal to 12 plus 20, which is 32 microseconds. And then if we do the math here, so this is in seconds. And this is in bits per second. Or but this is in bits per second. If it were 100 MBS, then it would be megabits per second. Remember, in this case, he wants the units in bits. So if we do 32 divided by 100 times 10 to the 6th BS, well, when you do this division, is this quite right? Let's see. Oh, sorry, not divided. This is already at so I meant multiplied. Let's just draw parentheses around that. Multiply it, seconds cancel. And what do you get? you get a unit of bits, which is what he requested. So keeping your units straight is normally the best way to figure things out. So in most cases, he gives you all the numbers you need to solve it, all the values. So you just need to figure out what values are important in what scenarios. So in this case, it was talking about transmission. So you should be calculating delays and then using bandwidth. So once you're done with that, the number you get is going to be X must be greater than 3200 bits for guaranteed collision detection. So that's just that value. Nothing too crazy. And then we have this last portion of it. For this network, is the maximum phrase size sufficient for CSMA CD? Explain. So this, as you can tell by the 1 point moniker, is basically just a you know it or you don't question. So he's asking, for this network, is the maximum frame size sufficient for CSMA CD? So we calculated a maximum frame size of 3200. Is this okay? Well, we said, actually, no, this isn't a you know it or don't. This is a pretty simple question. If we go back up, well, if you remember back to the problem, it'll say the maximum frame size being transmitted on this network is 1000 bits. Well, we have a problem here. 3200 is a little bit bigger than 1000. So is the maximum frame size sufficient? No, because the maximum frame size was 1000, and we calculated that we would need 3200 in order to have guaranteed collision detection. Therefore, no. The answer is just no. All right. Learning bridge time. This is always fun. I think learning bridges were on test 2 as well, exam 2. So if you want to look back at those exams afterwards, that's where these topics will be. Consider the following network where A, B, C, and D and nodes B1, B2, and B3 are learning bridges. And then assume the forwarding tables for the 3 bridges are all empty when the 4 transmissions below are made in the order indicated. After the transmissions have been made, what are the contents of the forwarding tables for the 3 bridges? Indicate a port interface on a bridge by using the numbers provided. For example, B1 has port interfaces of 1, 2, and 3. These ports are indicated by the numbers hovering over the line. All right. First transmission, A to B. Let's draw the line. All right, A to B. Well, what does A see? Or well, actually, in reality, we have to fill this out by what the bridges see. Well, what does the bridge see? Well, on this transmission, the bridge sees an interface. A's message comes in on interface 1. So we know that we can get to A through interface 1. Learning bridge stores it. And then it sees that on a interface 2, it sends a message out to B. So it stores it. And that's as far as we can go for now with that transmission. So next, D to C. Okay. Well, we only affected bridge 3 here. So bridge 3 now knows that its interface 1 is connected to C and its interface 2 is connected to D. That's as far as we can go with that transmission. 3, B to A. B. Bruh. Okay. Why
I don't
not?
know if that's right. So on
Which
that,
one?
both of them. So
Let's
on the
see.
first one, we're doing A to B.
Yeah.
The bridge 1 learns that A is on interface 1, but it doesn't know where B is. So it broadcasts that through all its interfaces.
I
So
think you're
then
right.
B2 will learn that A is on its interface 1. And then B3 will learn that A is on its interface 3.
I think you're right. It just shoots it out. All right, let's try that again. All right. A to B goes in here. B1 is now where that interface 1 is where A is located. As Seth said, it now broadcasts, since it doesn't know where B is, A's location everywhere. So it shoots it out this way and this way. And then does it broadcast, does it travel through the whole network or just its locals? It should just be its locals, right? I don't think B2 then cascades it down.
Well, yeah, B2 has received a packet that needs to be sent to B, but it doesn't know where B is, so it sends it on.
So you say it goes this way?
Yeah.
Anyone else have comments for this portion?
No, not
I
really.
think we're good here.
Do you guys, so you guys looked at this a little earlier, you said, do you know
did.
which way is you like to do it?
We haven't looked at this problem specifically.
Okay. We'll look through this. So you say it broadcasts everywhere.
Yeah,
All right. We'll just-
unless it knows the node or the interface that it's supposed to go to. Like unless it's already known,
Yeah.
it sends it everywhere.
All right. So A is now where, or B1 is now where the A is on interface 2. Bridge 2 knows that interface 1 is how it gets to A. So it stores that. Bridge 3 knows that interface 3 is how it gets to A. So it stores that. And that's all for now.
Yeah.
All right. Now let's move on to the next message send. I think this is how it works. I think you're right. All right. Next message, D to C. Okay, goes here and broadcasts to the whole network since at the moment C is an unknown node. All right, B3 now knows that it can get to D through interface 2. It then broadcasts everywhere. B2 is now aware that it can get to D through interface 2. And now B1 is aware that it can get to D through interface 3. And that's it for that transmission. Move on to the next transmission. B to A, do this. Now B knows where A is. Does it always transmit always or no? Because in this case,
It only transmits everywhere if it doesn't have.
yeah,
it in
yeah,
its-
no, that works. That works.
So it's only gonna
Yeah.
send it through interface 1 right now.
So it'll just send it this way.
Yeah, and
Yep,
the
so
rest
now
of them do
this
not
is
learn
aware,
B.
and from here on out, because B is no longer going to be transmitted to the rest of them will never know. There's that. So we have unknowns. So next message, bonk, bonk, is the last one, C to D. C to D. So it transmits here. So B3 is now where C is. It's on interface 1, but the rest of them will never know. And that's how it's done. And this question or this answer matches his solution spot on. Good catch, Seth.
No problem.
All right, so that's how that's done. So to reiterate, learning bridge problems, when you transmit, when the bridge is fresh, you transmit to all the nodes, and the only things that should be catching data are the interfaces, nodes themselves. These don't, B, C, whatever, they don't store data. That's not important. The only things that store data are B1, B2, B3, or whatever they're labeled as. And when a transmission occurs, it only stores that node itself. If I transmit A to B, the only thing that should be populated in that original message send is going to be sending it where A is across all of them, and vice versa. That's how that works. So, well, we'll just clear that. That's that question. That's that whole question. Easy peasy. A little confusing at times. Where's my doodler? All right, some short questions. So this is all just vocab stuff. So at this point, you should have a vague understanding of most of the vocab questions and be able to get at least partial credit on them, if not full credit by just bullshitting. But it's important that if you really want to like know all these, I recommend reviewing every single one of his vocab-esque questions from his old exams and the exams we've had thus far. He's bound to reuse the ones we've already had. And if worse comes to worse and you really want to know some stuff, go through his PowerPoints and just read the slides of vocab stuff, not of like concepts of just like vocab sentence stuff. So starting here, please explain what problems NRZ encoding scheme can be addressed. Please explain what problems of the NRZ, there's no the here, but of the NRZ encoding scheme can be addressed by the Manchester encoding scheme, So NRZ, now return to 0. Oh, yeah, even on his exam, it's not NRZI, it's just NRZ, as I was saying. NRZ, num return to 0. So your first problem with the NRZ encoding scheme that can be solved via Manchester is your consecutive zeros and ones. 0 plus 1. And he says problems. So he, in his slides about encoding, which is like, it's early on, it's got to be before test 1 stuff, because so it's got to be in the first thing. He just talks about it, just straight up, just has slides where he just talks about the problems and the fixes between them. So it's probably worth giving those a look if you have the time. But in this case, I'll just read his solutions for them verbatim and we'll just memorize it because these questions will basically be the same across the board. So in this case, consecutive ones and zeros is a main problem with NRZ that Manchester doesn't have, which is why it's addressed by it. And then the other thing is clock synchronization and baseline wander. Those are three different changes or these are three different problems that can be fixed by Manchester encoding. On exam 1, I think we got this question. I'm pretty sure. Actually, we can find that out. Let me pull the semester's exam solution up. Let me see if this question was on there or not. If it would load. All right. Well, it's because I'm doodling. So this is the exam that we've taken this semester. We're gonna clear that. And you can see what are the two problems of the non-return to zero NRZ encoding. We straight up had it, like the exact same question. And in this case, he changed the phrasing. So there are three problems he discussed in class, and he asked for two of them specifically. So you can pick from any of the three. In this case, he picked baseline wander and clock recovery. I remember picking consecutive ones and zeros and clock sync, which if you wrote clock synchronization, it would also count as clock recovery. So I just guessed for that and got lucky. But then other like quick questions, what's the efficiency of different encoding schemes? 8-bit to 10-bit is obvious. 8 divided by 10 is 80%. ME, you just have to memorize. And if you didn't have it memorized, you lose. But here's the thing. When you need to pull something out your butt, you guess 50% for efficiencies. 50% is super common. Just guess that if worst comes to worst. IP check, we'll go back to the actual other exam now. But, that's the NRZ stuff. We just discussed it. What is the purpose of bit stuffing or using stuffed bits in the HDLC framing scheme? Bit stuffing is because HDLC framing has a flag character, the pattern of which is 0, 1, 1, 1, 1, 1, 1, 0. This is a flag. So what you need to do is use stuffed bits to prevent more than 5 consecutive ones appearing, I believe is the rule. So you could answer this question a lot of ways, but his specific answer for this one on his solution was avoid this flag pattern to appear within the HDLC frame or the non-flag part. So this flag should not appear in your data. So you use bit stuffing to shove bits in. And I believe bit stuffing is done with zeros, if I'm not mistaken.
That sounds right.
But I'm sure if I were to click mouse and go back here, we had bit stuffing somewhere. If not here, it was in exam 2. No bit stuffing, no bit stuffing. That's VC. If there's not a VCI, or if there's not a VCI question on the exam that we're going through, I'm going to go back to this exam. We're going to go over that. VCI is big. No, okay. So exam 2 is where bit stuffing was. I know we did it on an exam. Bit stuffing, bit stuffing, bit stuffing, bit stuffing. Where are you at? Where you at? I might be wrong. I might have just misremembered it, or I might have missed it on the other exam. I'll go back one more time. No, he did 2-dimensional parity though, and some checksum stuff. Bonk. All right, so that's that. That's bit stuffing for HDLC. Why CSMA CD cannot be used in a wireless environment? Can't be used in a wireless environment because collision detection fails. So basically, let's think about the main problem with the 802.11 protocol, which is the hidden node problem. The fact that in a wireless environment, let's say I have a node here and I have a node here, and then I have a node over here, right? Let's say that their ranges are such that this node can communicate here and this one communicate here, but they're just so far apart that their messages will not reach one another. And let's say that both of these nodes have an urgent message for 1. This is node 2 and this is 3. They both say, hey, 1, I have something important to say. And they spam him with Discord mods, or they spam him with Discord messages, right? Well, 1's going to get overflowed, but collision detection operates by having 1 then emitting collision detection in the standard sense would mute the entire network, right? So you try to mute the entire network, except one also has a limited range. So functionally what it amounts to is there are nodes all over the place that one cannot silence because his messages won't reach there because they won't go too far. So you can't do collision detection. You have to do collision avoidance in a wireless environment. And that's the CSMA/CA, collision avoidance is what 802.11 uses. And that's like hidden node problem, all this other stuff. You can't get away with using collision detection here because collision detection has to propagate the entire network and silence everyone, where collision avoidance cannot do that because it's in a wireless situation and it can't always reach every network component. All right, there's that. What are the 5 tuples for any crypto system? See, so when it comes to crypto stuff, you're going to see questions like this, basically just vocab shit. So you just got to remember it. So in this case, what are the 5 tuples? Plain text, ciphertext, key, encryption algo, and decipher algo. Those are your tuples. That's what he says. So once
Is there an acronym for that?
PCKED.
Oh,
I mean, I would just do PCKED. Picked, I guess. If you want to make it picked, plain text, ciphertext, key, encryption, decryption. Those are your 5 key tuples. But as I mentioned, he has a lot, like the last like 3 classes, I believe, were straight up just definitions and information. Nothing that you'd have to calculate or do physically. So you're only going to see crypto stuff in this kind of question. Maybe a type of open-ended question asking you about crypto stuff, maybe worth like 6 points. I could see that, but most likely you'll get a couple of the questions like these quick 2-pointers that you'll miss out if you don't review. So you're going to need to go back through those slides and just quick read them, 30 minutes, 45 minutes reading through those slides. They're all short presentations. And you can block any of the stuff. You can just skip any of the stuff talking about the rigorous mathematics of doing the calculations, right? It's not necessary. But you're going to want to know AES. You're going to want to know the other one, which starts with an R, which is RSA. All those, right? You're going to want to know all of them, what they are, that kind of stuff. And in this case, well, picked is supposed to go down here, but even so, that's a quick acronym if you want one. But I would just, if you repeat it to yourself 3 times over, plain text, ciphertext, key, encryption, decryption, plain text, ciphertext, key, encryption, decryption, it'll be there. You won't forget it. It'll stick there long enough. Worst comes to worst, memorize it right up until he hands you that test on paper and instantly jot it down so you don't have to think about it. All right. What do we need to include in the timestamp or nonce information in device authentication? Yet again, this is a crypto question. So why do we need to include the timestamp in a device authentication? So this is to prevent the so-called replay attack. So a lot of problems in early like cybersecurity systems came where basically the replay attack is a type of man-in-the-middle attack, I guess, where let's say here's node A, here's B, and here's me, node E, right? And let's say node E, let's say here's our wire. Let's say node E cut the wire and connected a transmission that I have control over through this device, right? A sends a message. I pass it through. A is asking to authenticate. B says, all right, and sends back key. But then E intercepts the key, intercepts the message, manipulates it, sends it back such that when A responds to authenticate, A thinks it's talking with B or B thinks it's talking with A, vice versa, but they're actually talking with E. So I've successfully spoofed who I am by replaying their messages. So the timestamps are necessary to compare against RTTs and expected traffic times to prevent me from having the ability and time to craft a replayed message such that I can authenticate and impersonate another user. So that's why you need to include timestamps in device authentication stuff. List 3 techniques to achieve TCP congestion avoidance. All right. so this is just more memorization stuff. I don't even know this off the top of my head, but his solutions here is the DEC bit. The RED, whatever that might be, and then the source based approach. Functionally, right? So these are the three he has in his solutions. Now in reality, collision, no, it's not collision avoidance. Flow control is in TCP and it exists to prevent the receiver from being overflowed. It prevents the receiver's buffer from being overflowed. That's what flow control is for. But congestion control is a network parameter in TCP that prevents basically what amounts to packet loss because of an overly congested network. So everything here corresponds to some router device between nodes. So whenever you get a question like this, if you haven't like gone to the slides and memorized all the stuff, this all probably came from like 3 slides straight in one of his earlier TCP lectures, if you want to go back and just read through some of those. But just think whenever you see congestion, it has to, whatever it is, it has to talk about the router. So I'm pretty sure the deck bit is something the router can modify to say, hey, I'm congested. A source-based approach is some method by using the nodes connected to the router to figure out if congestion's occurring. And then RAD is some similar, parameter or option that allows you to figure out if something's going wrong. But basically, for stuff like this, for these questions, you're just going to have to either memorize them off of the solutions of the past or go through his slides. It probably wouldn't be a half bad idea to make a Quizlet out of his slides tonight or tomorrow morning and share it with your friends. That's a good plan. Let's scroll down to this next thing. So this is IP stuff. That's always fun. So this is a exam 2 topic. So we have a next hop and an address set. So right here, what is the next hop that the router selects when it receives the IP packets with the address shown below? Show all of your work and explain how you determine the next hop. All right. So here you go. Here's an address. Where's your next hop? Well, you'll notice that this specific address is not in any of them, as in it's not specifically any of these. Now, what does this mean, this address / mask? Well, what it actually is it tells you that these are address ranges. So basically you have to figure out if this address falls within any of these ranges. Well, let's look. 135.46, 136. Well, it can't be in this range. And it can't be in this range. Or no, it can be in the first range, potentially. We'd have to do the math. It cannot be in this next range because we've already passed 136. So we check this address right here. And basically 135.46, they're identical. So far, so good. 64, 136. Well, we have 64, but we have the 20-bit. Now, addresses should be 32 bits long, I believe. Right? Is it 32? Yes. Should be. Wait. I don't remember how long IP addresses are. It should be one field is 4, next field is 4, next field is 4, next field is 4. So it should be 16 bits. Sorry, it's 16 bits, not 32 bits. 16 bits long. No, that's not right.
Huh? Isn't it 3?
How long is an IP address in bits?
Oh, in bits.
It looks like there's 5 fields and they're 4
Yeah,
long.
8 times 4 is 32.
It's 5 fields.
Since when?
Right here. It's 5 fields. 5 fields of 4 bits.
The 5th field is the subnet mask.
It's a /20.
I don't think that counts as part of the address.
No, it doesn't.
No. So it's 4 fields, so it's 16 bits, right?
30.
Anyone all right. 32?
Yeah, it's
8
32
times
bits.
4.
Oh, each of these can go up to 8. Oh yeah, I see what you mean. Oh yeah, I get it now. All right, I see what happened. I boonked up. It is 32. So whenever you have fields that are the same, you can just X them like he does. So 135.46, they're the same. So you don't have to consider them. 36 or 136 and 64 defer. So now you have to try. So you convert 136 into bits, which happens to be 1000, I think. No, that's not quite it. It's 1001000. That's 136. And looking at that, you'll note that 164.0-20, this number is out of range of the highest value that can occur from this address. Because the highest value that this address can create is, let's assume this is the same, this is the same, 0, 1, 0, 0, 0, 0, 0. It's 5, 6 zeros. 0. Because you convert 64 into binary and you have your field of 8 here, and this is the peak field it can produce. Wait, is it the peak field? No, I think that's
That's the first index. The peak
Yeah.
field would have all ones after your
first one.
4 digits there. So it'd be 0, 1, 0, 0, 1, 1, 1, 1. And then the last 4 that we don't have written out would be 1, 1, 1, 1.
Yeah, but even so, this is out of range.
Yeah.
And this is bigger than this. Therefore, next hop has to be your default hop, that being R3, which is correct. Yeah, I just had to refresh my memory on this. All right, next one.
Wait,
136.46, still the same, but we have a
Why did-
255.
why did the .176 not work?
.176 is bigger,
Well, yeah, it's bigger, but
but remember,
fine.
no, it has to contain it within its range.
Well,
So
I mean, as long as it's not bigger by more than 15.
well, no, that is like, remember like we just determined that this value is the minimum of its range. And then the 20 lets you go up to the highest peak of its range, which is the all ones version. But that problem means that 176 is bigger than 136.
No, so only the first 20 bits must match.
Yep.
So let's say, so anything between 128 and what is 128 plus 15? 38, 143. Anything between 128 and 143 would work. So
Well, his
what I
solution, his
what I mean to
solution
say
has it
is-
dying out and going to 3.
huh?
He has it going to the default. It's not in range.
Well, yes, it's not in range, but I'm going to annotate the screen real quick. So if our last digit,
I
or
can't see it.
I haven't written anything yet.
Oh, okay.
So let's say this value right here
Mhm.
is, forget it's 176. I want to say it's 128. So that is 1 0 0 0 0 0 0 0. Now we have 16 bits beforehand, and then it's dot, and then it's this. So this 20 right here means that the first 20 bits have to match. So we have 16, 17, 18, 19, 20. So it literally does not matter what's here. These can be all zeros. These can be all ones. Doesn't matter as long as these 4 are the same. So this any value for our third octet here between the range 128 to 128, where all these are ones, which is 15. So it'd be 128 to 143 would in this value would fit a .128 here. I don't know. I didn't say that quite right, but
Well, yeah,
know what
but
I mean,
I guess so. But in this instance, since it's 176 and it wasn't in range for this prior number, it won't be in range for the next one because 176 surpasses 136.
yeah. Well, 176 isn't in our range here. So what is 176? Let me pull up my calculator. The 176 is 1011000. We can forget about these since the 11 does not match the 000. Like it differs right here, and that's why it doesn't.
Yep. Makes
But
sense.
if it differed anywhere here, then it would go.
Yeah, then it's within range, then you're fine.
I don't remember why we disagreed on this.
I'm not really sure either.
All right, I'll just erase my stuff.
Well, I'm gonna clear it's the whole thing, all of it is messy.
All right. My bad.
R3, oh, no problem, R3, and then over here, we're looking at 255, our third octet. So we gotta look, well, there's a chance that this might just work, but it's a fat chance. So basically, he's got it where you do this out. What is 255? 255 is going to be 111111111, right? This is the 4 that don't change because this other stuff where you're, 8, 16, this brings you to 20 bits. Now over here, router 2, let's bring this out. That's the same, 240. What's 240? Well, 240 starts out being 1111.000. So they're the same. Therefore, as Seth put it, we do get to go to router 2 because these numbers agree. So it doesn't matter. It's within range on the other side. So you're good. Moving on to this next one. So we have 73. So 73 is 0100 as our octet. That's a 0. So let's look at this. 73, what number does it look like it's going to match? Well, we already know it's probably going to match interface 0 because 73 is crazy close to 64. But let's look at it. 64 starts out 0100 as its 4 following its first 2 octets. Therefore, boom shakalaka. There we go. Boom shakalaka. We have interface 0 as our target. Clear the drawings here so I can move everything down. Last 183. 183. Yeah, 183 0100. So here's our 4 after the first 2 octets. So looking back up at our interfaces, 183 is crazy close to 176. When you do the range math, 176 turns out to match. Yep, so you just go to I1. Easy peasy. And clear. So that's how that's done. Next. Sliding window. Let's get it. All right. Bonk, bonk. All right. Consider a network where the sliding window protocol is in use with sliding window size is equal to the RWS. Anyone remember what RWS stands for? It's a window size. Receiving window. Yeah, there. Yeah, you're right. So sending window, not sliding. That's sending window size is equal to receiving window size is equal to 2 frames and a one-way delay of 100 milliseconds. I.e., for a frame sent at time t, it arrives at t plus 100 milliseconds. And it's a one-way delay. Assume that when multiple frames are all able to be sent according to the window size, that they are sent 20 milliseconds apart. One frame starts at time t and frame 2 starts at 20 milliseconds or t plus 20 milliseconds. What will be a reasonable timeout value for this link? And then he asks you to qualify some more questions here. So he said we have a one-way delay of 100 milliseconds. So if that's the one-way delay, that means the RTT is equal to 2 times 100 milliseconds. Okay. Well, if we set the timeout value equal to RTT, it's too small. It's not going to account for any type of congestion, stuff like that. So what's going to end up happening is that that's a little too small. So what we want to do, well, basically, he says, what would be a reasonable timeout value for this link? So you kind of just suggest something. So the thing that I've been saying is 1.2 times the RTT value. But really, his solution, he recommends to say 1.5 RTT, but really anything from 1.2 to 1.5, that range is probably acceptable. When you start going double RTT and bigger, you're just wasting time and sitting there idle, doing nothing. It's not worth it. So basically what he says, why not something smaller? The problem with something smaller is that you might have a false retransmission. And why not something larger? As I just mentioned, waste of resources. Why sit there idle when you could be talking, right? So that's that question. Can the selection window size equal to 2 fully utilize the link? If yes, please explain. So he draws a diagram to help with this. So we have S, we have R, and we have a send, a receive, and a send, a receive. He notates that this, as mentioned in the question, is a 20 millisecond delay between sends and a 200 millisecond delay for the total send receive RTT of a system. So basically, the selection window size being equal to 2 fully utilize the link. Well, let's think about this. He has sent 2. This is the sending window size is equal to 2. So he just sent 2 messages. It takes 20 milliseconds to send a message, or there's a 20 millisecond wait between message sends. That means there's 180 milliseconds of space between the first send and the first receive sitting there idle. What does that mean? Well, basically, if you do the math here, it's going to be 20 divided by, oh wait, no. It is 200 divided by 20 to find the maximum amount of packets you could feasibly send. 200 milliseconds divided by 20 milliseconds is equal to 10. In theory, you can send 10 packets in this window. So you could have a window size of 10, but we send 2. So our efficiency is 2 over 10, an abysmal 20%. Don't do that. You're stupid. That's not a good plan. So your answer is no, and you point to the shitty efficiency. Did I just stop screen share?
No, you're good.
Oh, I accidentally put away my annotate. That's what I did. All right, clear that. Go down. Bonk. 5. Now assume that by sending a frame every 5 milliseconds, we can saturate the link. In this case, determine the smallest sending window size and receiving window size that maximizes throughput, aka keeps the pipe full. All right, we have 200 milliseconds of space between a send and a receive of a single message, divided by the new 5 millisecond delay for saturation, and we get a sending window / receiving window size, not 48, of 40. Unitless number. That's basically all he says. And this is all it took. So all that space for one fraction. You know, sometimes he likes to juke you, make you think you got to do more work than you need to. But that's all you need to do. So that sending window size question is rather simple. All right, link state. Fun. These are always a blast. All right, easy to make mistakes on these. Link state. The link state routing algorithm, I think it's Dijkstra's or forward search algorithm, is performed for node D. The link state packets sent by the nodes in the network are shown below. Cost is measured by the throughput. Okay, that's important. So throughput, is it additive, multiplicative? That's the trick with these. The reason these can be tricky is based on what the cost is measured in. If it was delay is additive. I think throughput's lowest, just the floor. So if you have a throughput of 2 paths to get to a thing, you take the faster one. I don't remember.
Throughput would be like the amount of data that goes through it.
So when you start chaining that
sending-
together, I don't remember if it's multiplicative or additive.
I don't think it matters since we're only sending 1 packet.
Yeah, we'll see as we go. We'll find that pattern pretty quickly. Cost is measured by throughput. When finished, provide the routing table for node D. Link state packets are in the form of destination, cost, next hop. Use the link state packet form for completing the information below. You must use the algorithm in the space shown below. Cool. So you use all this space to figure stuff out, and then you end it by filling the table with your final results, which should be what you see in the last row here. So let's clear the doodles that are there thus far. All right, right now we start at node D. What can node D see? Well, there are no confirmed nodes as of yet, but node D 100% can see these two nodes. So what do? You just copy them verbatim. Nothing crazy. Easy points on the start. Nice partial. Good partial on these questions. All right. Next thing's next. Yeah, pick a node to confirm. But normally, the way that he picks a node, since we're using throughput, is you go for the higher number. Normally, you would use delay and you'd go for the lower number. So if our measurement here was delay, we would do E2E because 2 is smaller than 4. But throughput, you want the higher the values to select which one you want to confirm first. So we're confirming B because B has the value of 4. So now we've confirmed B. We move it over here. Cool.
Is that what the answer said?
Yep.
Huh.
Well, he did it that way. That's my assumption as to why he chose it. And he continues to only choose the highest numbers on confirmations.
All right.
I guess that makes sense. So now we've confirmed B. What does that mean? It means we jump to B and consume any of these and add them to the tentative that aren't already there. If they are there, we're going to have to choose which one to keep. All right. So first things first, E is still on the tentative list. As you confirm nodes, cross them like that. It's a good mood to keep yourself not making mistakes. So you do that. So first things first, any unconfirmed nodes that are tentative immediately just get carried on down with no modifications until something modifies them. So E2E, next we carry A3A and C5C in. D4D is unnecessary since we're starting from node D. We don't need to take it. You can actually cross it out immediately. Whenever you see a D, you can get rid of it yourself, right? You can simplify this right off the bat and cross out the Ds. Since we're starting from node D, nobody cares. All right, there's that. So now we add A3A and C5C. Cool, cross. Now, next state, you carry down confirmed nodes. And now you have to pick the next node to confirm. Wait, what the fuck? Sus. I'm confused now. So he copied in his solution. When he went to node B, he took C down as a 4 when it's obviously a 5.
It doesn't matter because either way it's the highest. But you need to add the cost of B to these, the cost of C and A. So C is actually
It's not
8,
added. It's not.
It's actually
no.
9, and then A
It's not I think I was right earlier based on his answers. It's not additive. It takes the floor. It's throughput. So it's the pipe. Let's think of it as, you know, the pipe's maximum width. Let's say it's me restricting the pipe. So let's think of E2E as a pipe with a width of 2, and then C5C of a pipe with a width of 5. Well, if you're sending data along this chain, where's your limiter? 2. So you carry in the lowest along the chain. So instead of copying C5C, we went from node B to, we went from node D to node B. We went over here. B, we traversed to B through a link of 4. So 3 doesn't change. We don't take D. C's a link of 5, but since we traversed via a link of 4, the 5 is replaced with a 4 because our limiter is the pipe of width 4 instead of width 5.
Oh.
So it was the floor value. I knew it. I had a vague recollection of how it works, but that's the trick. He can confuse you on these problems by changing a single word, the cost measure, delay, throughput. There's another one that's multiplicative, which is efficiency, I think. Like, it's really wacky. So you got to pay attention and figure, and you got to know how to carry your, calculate your costs through, because otherwise you just get L's on everything. But continuing on, if that's the case, it's still the highest here. So we confirm C and jump to node C. So now we're jumped to C. We just came from B, so you can auto cross B off. You don't need to know that. And now we can cross C off here since we've just confirmed it. And we carry down these two and add what's here, F. So now we have F6,
No.
F.
It's not
not.
C4C, it's C4B.
Yeah, because we jumped from B. That's the next hop. And I just made another mistake. It's not F6 F because we came from node C as a limiter of 4. Therefore, F now has a limiter of 4. And it's also B. And I have to change this one earlier. This is where the B changed originally in the tentative.
And on A.
Yes.
Yeah.
E doesn't change. E is still E because we haven't done any modification to it. This is meant to be a B. F4B. That, and then there should be this A3B. From here on out, I'm just going to draw arrows down. I don't need to keep copying like that. You could probably speed it up that way in that's probably a good way to optimize the process. But there's that. So that's all that one now. So now you move on to the next one. Pick the highest of the values. It's the F4 one again. So now we carry this down, and F4B is now carried over. And now we go to node C. We'll cut C out there. We're done with F. Node F over here has a couple of things. So we already have an A, so we don't need this. And we already have a C. So that's where we came from. We also don't need that. So node F is just a dead end, but we still have to record it. So node F, we've added no new ones to the tentative list. Yeah, added no new ones to the tentative list. So we carry down A and E again. So now on the confirmation list, we confirm A and carry down these other 3. And now we go to node A over here. B and E get crossed off instantly. And same with F. Node A is also a dead end. So we've added nothing new to the list. So node A is just confirmed. Where did it go to 4? Somewhere along the line, node A went to 4 instead of 3. So let's think. It's 3 here. It's 3 at this level. But then it goes to 4 here. So let's think about that. The node that we were operating out of here was C. Oof.
Wasn't it F?
But yeah, F. So we have F, which has a path of 15 to A. And I don't know. I don't know why it changed to 4. When worst comes to worst, by the way, when you're looking at these, draw the network and the lines. Like, that's not a bad strategy. What'd you say?
Wouldn't node F be where A goes to 4 because you have the throughput max of 15?
Yeah.
But we make it 4 for the same reason before because we had a previous node that had 4. So it's a max of 4, but 15 allows for that whole 4 throughput.
Oh yeah, let's see. Let's traverse. Yeah, because F has 4. Yep, that's why. Because it has a new path that can surpass your throughput. So you reach the floor of the available values now, which is 4 instead of 3. You're correct. So at F is where this becomes A4B. So then down here you confirm A4B, but as we know here, that doesn't change any values because we've already confirmed the other nodes. And then all we have left is E. But E changed because we have a new path to E with a higher throughput here, which is 3. So now it's E3B. It's finally not E2E anymore. It's E3B. And then we confirm it, and that's it. So the final routing table is a cost of 4 all around, except for E as a cost of 3, and then a next hop of B for every single one of them. There it is. Throughput ones are definitely the trickiest type. But remember, worst comes to worst, if you want to solve these questions with almost 0 brain effort, you just draw the network physically. So, worst comes to worst, right? Down here. Oh, this is the beefy one. Pretty sure it's a different question, right? Somebody mentioned that the question,
This is like the one on our
If you look at the
homework.
solution, this one asks different questions for like A, B, C, and D. They're different questions on the solution.
yeah, you're right. So we'll operate off of the solution. All right. So big old block of text that I really don't want to read right now. So we're just gonna think about, we're gonna have to read it. You don't have a choice.
The block of text has some differences in it too, just by the
Yeah.
way.
All right. We have a TCP connection that goes through router A. AR link has infinite bandwidth and a 1 second prop delay. RB link has infinite bandwidth and 0 prop delay. Always helps to draw the figure. Router R has infinite buffer size, while node B has a finite buffer size of 8 packets. Node B's application reads 1 packet out the buffer every 2 seconds, but only reads data in sequence. For example, if P1, 3, and 4 are in its buffer, B's application will not read P3 after reading P1 because P2 is not present. Once P2 is recovered via retransmission, P2 can be placed at the front of B's buffer and read first. Nodes B sets the advertised window at most half of its available buffer size, which means the largest advertised window for B is going to be 4, since we know its buffer size is 8. Keep that in mind for the future. For example, if there are 300 packets at B's buffer, the advertised window equals to floor of 8 minus 3 divided by 2 is equal to 2. So that's the formula for it. The information of the advertised window size is piggybacked on the ACK, so you don't need to send an extra thing to tell them about the advertised window size. Router R instantly forwards packets, so no prop delay across the router, and ACKs to B and A respectively. B's acts every packet it receives. B acts every packet it receives and adopts the repetitive ACK, i.e. repeating the ACK for the received packet of highest sequence number. For example, if P1, 2, and 3 are received by B, it returns ACK 1, ACK 2, ACK 3. ACK 3. If P2 is lost while P1 and 3 arrive correctly, B sends ACK 1, ACK 1. So that'll let you know that P2 did not arrive, but P3 did.
What I don't get is that if the link between R and B has infinite bandwidth and 0 propagation delay,
Yeah,
it's effectively the same device. So why even include an R?
to be funny.
All right.
just to make the figure look cooler. You see this figure with a lion? That's what infinite looks like. It's a straight line.
Yeah.
That's why. I guess. Really? I think I don't know. I really don't understand it either. It's just to make it more complicated, I guess, so you understand the topic. The funniest thing about it is this does not exist. So, you know. Yeah, it'd be like that. Where was this? It was here. Yep. All right. Honk. Yeah, so that's repetitive ACK sequence. So we should be very familiar with repetitive ACK by this point. We've done it a million times. All right. And here's the important part that I lost points on because I'm a loser. Upon observing the 3 same ACKs, including the first ACK, if A fires retransmission right away without waiting timeout. I lost points on that for exam 1 because I'm a loser. All right. That's actually the only points I lost on exam 1. Cringe. All right. Host A process information in the following order. First process any ACKs, then process any timeouts, and then send more packets if possible. The whole processing takes 0 seconds. In normal situations, session live and no timeout, host A always sets its sending window size equal to the advertised window size. When timeout occurs or receiving 3 ACKs, host A drops its sending window size to 1. The initial sending window is 1 packet. The timeout is 4 seconds. Suppose B's application starts to read out data at t is equal to 3. In the first packet, P1 sent by host A occurs at time 1, and P4 is lost in the first transmission attempt. Please answer the following questions. So now we will clear all of that. All right, let's look at the doodle. Time 1 is when P1 is sent. P1 is sent to the router. The router instantly forwards it to B. No problem. ACK is sent back, ACK is received, and it is received at 3 seconds because that's what the network said was going to happen. B's application starts to read out data at t equals 3 seconds. So it doesn't start reading data in until you get here, which is what it says. So we receive the ACK back, Because there is, I believe it's 1 second of propagation delay. Yeah. So it's received back. And then we send the next one. Which immediately, since it received ACK with no issues, jumps to 3 in 1. Because we can send multiple at a time now, based on the sending window size. So you see it sends P2, P3, and a failed P4. So we send it and we get Act 2, Act 3, and then it should be Act 3 again because P4 failed. So we get Act 2, Act 3. It sends P5, P6. Sends it, receives it, gets 2 Act 3s back. That's 3 Act 3s in a row. Retransmits P4 because it receives 3 Act 3s in a row instantly. P4 is received. Act 4 is sent out, received. And now we go back because 5 and 6 were sent, no issue. P7 and P8 are now sent, and you just do this. It looks like he could have just kept going, but he didn't need to. So I guess just go up to like 10 packets. That's what he did. So you'll note that he kept sending packets, just one less, because the sending window size was dropped until he received so he received the Act 3 back with this original because they received 3. Yeah, 1 Act 3 back because 4 wasn't received. And then when you receive 5 and 6, you get 2 more Act 3s, sums to 3, instant retransmission to 4. That's the trick here. You can even see that the professor made a mistake himself in this solution because he had to cross out. You can see he used to say 2 Act 3s, but that's not the case because P4 never arrived. Therefore, it doesn't know to send an ACK. It only sends a repetitive ACK if an out of order packet arrives. It doesn't send it if a packet never arrives because how would it know to send an ACK, right? So that's how that works. So this is a pretty simple thing. It just looks complicated because he added another line. But really, as Seth said, this is functionally no different than if it were just A to B. With infinite bandwidth and infinite transmission time, there's really no change to the network topology here. The router just makes it funny. You have to add another circle. But that's about it. So that's the exam. Any specific questions? Because I'm going to go get pizza or something. I'm hungry. Hello, gamers.
I don't have any questions.
No questions, no questions. How about you guys on the Boone Perkins account? You guys have anything you want to bring up specifically?
We're all right on this one so far.
Yeah, I think we're good for now.
Yeah. Well, this is probably as far as I'll go because this one, I think we started it at 8. It's been about an hour and almost a half. That's normally the cap I put on these. No one wants to look at the 2-hour YouTube video.
Pretty true.
So closing argument here, because we're in court, obviously, is
You should
functionally.
monetize it.
You can't monetize a channel unless you get a certain amount of subs and views.
You
And
should
I
do
actually, that's the
bots.
thing, I actually legally can't monetize it because I email all the professors and make an agreement with them that I won't profit off of their work because I actively use their notes and their solutions. So I cannot monetize it ever.
Oh, dang.
Yeah. So if I ever like posted stuff on the YouTube channel that was personal, that was monetizable, I would have to either delete or hide all of these videos.
It's called plagiarism.
Basically, yeah. But it's if you ever want to make videos like these and post them for benefit, it's not required necessarily, but it's because most professors don't mind, but it's always good to reach out just in case. You know, that's just how it works. But you know, closing thing, go back to your old exams, whether both of the ones we took this semester, along with the ones in the past, and memorize these shits. All these little 2-pointers, they look like, oh, it's only 2 points, only 4 points. How much could that be? Yeah, it's worth 14 points. It's a lot. It ends up being worth the solid 20% approximately of your final grade, and they're all gimmies. It's not worth missing questions like this when you literally could have just made a Quizlet and memorized them, you know, an hour beforehand. You don't even need to spend that much time dedicating your efforts. So go through the slides if necessary, but you can get away with just going through old exams and looking through all the 2-pointer, 4-pointer.
There are any Quizlets like that or no?
What?
Do we know if there are any Quizlets like that or no?
No clue. I definitely haven't made any. There might be some from the past, but I wouldn't trust them. Quizlets aren't that hard to make. I recommend just gathering all the exams and just literally just taking the question, typing it out, and typing out the solution, and then just flipping through the Quizlets. If you do make a Quizlet, I recommend posting the link to the Quizlet in the CPE Discord to be a gamer to the rest of your fellow CPE 348 gremlins. It's very important. But that's that. So get your memorization on these. This is worth a lot, and you don't really want to miss it because it's really not hard shit. You know, it's just memorizing stuff. There's no
I
work.
recommend posting that Quizlet to the Discord and not the one specific for this semester's class. So that way students and
Oh, you mean the
future
other one?
semesters
Yeah.
can see it.
There's another Discord called Surviving ECE that you can post it to. But for now, in the immediate future, make sure it gets in the CP 348 Discord for the people in the class explicitly, and then probably repost that. But honestly, if Seth has it, I know he's a mod or an admin on that server, so you'll probably repost it. But that's that. Go through. There's a couple other types of questions. Like I recommend going over like our old personal finals we took this semester. That's more like the stuff we're likely to see. CRC, we did that, right? Easy. You know, here are some joke questions. Check some, remember? Like little things like these. It's worth 3 points. It's not hard, but if you don't remember the procedure, you can get it wrong. Same with, you know, this is worth 5 points and it's just a 1 and 0 Sudoku puzzle. Like it's good points that you don't want to miss out on that really aren't worth missing out on. So make sure you still review back through these little things. You know, the solutions are there. This is network topology stuff. We did that, but still look into. Go back because everybody got bamboozled on exam 2 with this. Fragmentation. Make sure you go back through and make sure you have fragmentation down because you can throw fragmentation into almost any network topology question. So make sure you have your fragmentation down, like the rules behind how fragmentation operates, right? Because a lot of people made mistakes on that one. VCI, I mentioned it, but we're not going to go over it here because I'm hungry. But VCI is big. We did Dijkstra's algorithm, we did learning bridges, and the other thing is VCI. Those are the 3 like fill-in table questions that take up a page and are normally worth like half your grade or a third of your, or like not like a fourth of the grade kind of thing per exam. So I honestly wouldn't be surprised if we saw all 3 of these: VCI, Dijkstra's, and learning bridges. I wouldn't be surprised if we see all 3, but I would put emphasis on learning bridges and Dijkstra's algorithm. VCI isn't as important. It's an exam 1 topic. We didn't touch on it too hard, but it's also not hard enough to justify missing. Like it's pretty basic stuff. He gives you the network drawn out for you straight up, along with switching table. So just review how to do those. More protocol stuff. Yeah, RTT stuff. Yeah, so that's basically the rundown for this exam. I don't expect that it should be that bad. I don't think he ever ended up needing to post the 3rd bonus assignment because we've been doing pretty decently as a class on his stuff. Unfortunately, I don't know if the time limits, actually, no, I do know. The time limit for the SIE is up. If you haven't done them yet, that's kind of an L. You just missed out on some fat bonus, but that's unfortunate. That's just that. So I'm going to stop it here. Everybody, good luck on your exams. Have a good night.
You too.
See you.
Thank you. Thanks, Ethan.
Thanks.
Yeah, thank you.
Yep.